Hello, my name is Isaac, and today I'm going to be working through practice problem number 4 from Chapter 29. It has to do with the Bayat-Sabat law. And I've got it drawn already, but everything else I wanted to walk through with you guys so that you could kind of get a feel for kind of the logic of this integration. So what this is equal to is this is equal to the B field caused by some current carrying wire on some particular point P. Now in this problem, the current carrying wire comes up with current, takes a 90-degree turn and goes away, and point P is parallel with this length of wire and at the same height. The thing we're going to go ahead and do here is we're going to take each segment on its own and then see what happens. Let's start with this one, the current going this way. So this formula includes a ds cross r hat, and ds as a vector points along the segment length, and you always want ds to point in the direction of the current. And so then the r hat vector points from ds back to the point that you're interested in. And then you'll also realize that the length r is different than the r unit vector. The r unit vector is of length 1, whereas the r itself is the distance from the point to the ds curve. And so like for this segment of wire, r is some number, ds is pointing this direction and r hat's pointing that direction. And so the first thing to look at in this integral is to see what ds cross r hat looks like. Ds cross r hat is equal to ds sine theta, and that theta is the angle between ds and r hat. The reason why we don't include r hat in here is because it only holds direction. It's of length 1. So ds sine of 180, because you'll see here ds is pointed that way, r hat's pointed that way, that's 180 degrees, and sine of 180 is 0. And so we've now proven that this whole length of wire has a 0 contribution to the B field at point P. So we already know that B caused by this length of wire is equal to 0. Now we just need to know what B caused by this length of wire is. And then once we know that, of course, the total B at point P will be B1, which we found was 0, plus B2, which we're going to solve next. And so we're going to pick an arbitrary ds as long as it points in the direction of the current. In this case, r hat points this direction. We know that P is x away from this 90-degree turn, and so it would be safe to say, let's go ahead and call this length from the top down to our ds, we'll call that length y. And we know that r, due to Pythagorean theorem, is going to equal the square root of x squared plus y squared. So we've now solved for r. Now we need to figure out the angle between ds and r hat. And in order to do that, we could, for example, we could say that it's opposite over hypotenuse, because sine, well, let's do it this way. ds cross r hat equals, once again, ds times sine theta. And sine theta for this triangle is going to equal opposite over hypotenuse, which is r, and we solve for that. It's the square root of x squared plus y squared. Alright, so now that we're at this point, it's also important to realize that ds is going to be interchangeable with dy, because for this length of wire, the ds is always pointing in the y direction, and so we can then just go ahead and rewrite this as dy sine theta, which is now x over the square root of x squared plus y squared. So let's go ahead and plug this all in there. Alright, dy times x over square root of x squared plus y squared. So now we're going to plug it back into this formula and find that B2 is going to equal to mu sub naught, the permeability of free space, times the current in the wire divided by 4 pi, and then the integral of ds cross r, which we decided was equivalent to x dy over the square root of x squared plus y squared. But also, we also divide by r squared. Well, r squared is the square root of x squared plus y squared, so we can square that and find x squared plus y squared. So now we have it written in a form that we can handle. We can combine the denominator of this integral. Let's go ahead and do that real quick. Because something to the power of 1 times something to the power of 1/2, we're going to add them together. So that's x dy over x squared plus y squared to the 3/2. And that's where we're at now. I'm going to go ahead and get rid of the picture to make some room. Alright, so here's our integral. This is what we have to analyze. You'll notice that x was a constant in our photo. X was always a fixed distance, so it can be pulled outside of the integral. So let's go ahead and do that. Mu sub naught I times x divided by 4 pi integral of 1 over x squared plus y squared to the 3/2, and we're integrating with respect to y. This is looking a lot like we're going to be using trigonometric substitution. And so let's go ahead and do that now. We see that we have an x squared and a y squared. Any squared plus another squared is going to point us towards using tangent. And so we're going to go ahead and say that the variable y equals x tan theta. So we always want our variable to be on the left side of here and our number to be on the right side, because all that x is it's just a number. It's a fixed number. If you look at your picture, you'll notice that. So dy is going to equal, well, let's see here, dy, alright, so, oh, okay, my bad here. What's going on? Well, we do know that we can divide x over and take the arctan and show that the arctan of x over y is equal to theta. We can also say that dy d theta, oh, there we go. Okay, so dy is going to be equal to x times secant squared of theta. This is dy with respect to theta, because x is just a constant. Then we can multiply over the dy, and what we end up with, or we can multiply over the d theta, and this will be our substitution for dy. And so, now that we have that substitution, what we can do is we can plug in what our substitution is going to be. And for this part, I'm going to go ahead and ignore. I'm just going to carry down the integral, and then we'll plug that stuff back in later. So the integral we're looking at is x squared plus y squared, which will be x squared tan theta. That's all to the 3/2, all over 1 times dy, which we found was x secant squared theta d theta. And so this is now our new integral. And you'll notice inside here that you could pull the x squared out of both terms, and you'd end up with 1 plus tangent squared, which is equal to secant squared theta times x, which is still in there, x squared to the power of 3/2, and that's all underneath x secant squared theta d theta. Alright, so now we're going to go ahead and square and cube, or cube and then square root this term. 2 times 3 is 6 divided by 2 is 3. So what we end up with is x to the third secant third theta. And on top of it we have x secant squared theta d theta. And so the x's will cancel to x squared. There will be a secant in the denominator, secant theta. Now, if you'll recall, secant is defined as 1 over cosine. So we can go ahead and write this as cosine theta over x squared. Well, remember, d theta, I'm sorry. Remember, x is a constant, so we can pull it out. So let's go ahead and write the whole thing now. Now we have mu sub naught I times x in the numerator divided by 4 pi x squared in the denominator, because we pulled it out from here, integral of cosine theta d theta. And so the x's cancel, and what you end up with is an x in the denominator. The fun part here is we don't actually need to substitute back, because if you recall that picture, our wire was like this, the current was going that way, and the point we were analyzing was here. And so what we can do here is look at our angle to ds. There's our angle. Now you'll notice that when we are flush with this corner, that our angle will be 0, and that our angle will be 90, and then when we slide ourselves out all the way off to infinity, because this is an infinitely long wire, that angle is going to get very close to 0. So we're going from pi halves. We're starting here and we're going to 0. And so now what we do is we take the integral of cosine, which is equal to, you can see this problem takes a lot of time. So the integral of cosine is negative sine, or I'm sorry, it's regular sine of theta. We're analyzing it from 0 to pi halves. And on the outside of the integration we have mu sub naught I divided by 4 pi x. And sine of 90, or pi halves, is 1, minus sine of 0, which is 0. So this all just goes to 1. And what we end up with is that the B field caused by this length of wire is equal to mu sub naught I divided by 4 pi x. And that is not necessarily a trivial result, because if you recall, you can derive using this law the current caused by an infinitely long wire in both directions on a point.